every type of exoplanet atmosphere. Space is complicated. We make it simple. An atmosphere isn't just weather. It's the single biggest clue astronomers have for figuring out what a planet trillions of kilometers away is actually like without ever being able to send a probe there. Every category on this list is a real, directly measured, or strongly inferred type of exoplanet atmosphere. And every single one of them reshapes what habitable, hostile, or even planet actually means once you leave the specific narrow conditions Earth happens to provide. We're going in order from the most Earth like to the most alien, then we'll sort them a second way by what actually detecting each type required. Because on this list, some atmospheres were confirmed with existing technology, and some pushed our instruments to their absolute limit. Thin Earth like atmospheres. We begin with the category every exoplanet search is ultimately hoping to find more of, and also one of the hardest to actually confirm. A genuinely Earth like atmosphere would be thin, dominated by nitrogen with a meaningful fraction of oxygen sitting at a pressure and temperature that allows liquid water to exist stably on the surface. Here's the fact that should genuinely bother you. As of now, no exoplanet atmosphere has been unambiguously confirmed to match this description, despite thousands of confirmed exoplanets and dramatic advances in the instruments used to study them. The technology required to directly analyze the atmosphere of a small rocky planet orbiting at the right distance from its star is only now reaching the sensitivity level needed to even attempt the measurement. Here's the part that lingers. Several rocky exoplanets sit in their star's habitable zone, the orbital distance where liquid water could theoretically exist, but being in the right place and actually having the right atmosphere turn out to be two completely separate questions. And confirming the second one for a genuinely small, Earth sized world remains right now at the very edge of what current telescopes can achieve. Thick, Venus like runaway greenhouse atmospheres. Here's the twist: get the distance from a star even slightly wrong, and an otherwise promising rocky planet can end up trapped in one of the most hostile atmospheric states known. A runaway greenhouse atmosphere occurs when a planet's surface starts warm enough that water evaporates into the atmosphere faster than it can rain back out. And since water vapor is itself a greenhouse gas, that evaporation traps even more heat, evaporates even more water, and spirals into an unstoppable feedback loop that only stops once the entire ocean has boiled away into the sky. Here's the fact that should genuinely bother you. This isn't a purely theoretical hazard. It's Venus's actual documented history, and current models suggest Venus may have once had liquid water oceans, similar to Earth's, before a runaway greenhouse effect, possibly triggered by a shift in solar output, permanently transformed its climate into a crushing 90 times Earth pressure atmosphere of carbon dioxide, with clouds of sulfuric acid, hot enough at the surface to melt lead. Here's the part that lingers. Several confirmed exoplanets orbiting close to their stars are strong candidates for exactly this fate, and the boundary between warm and potentially habitable and permanently catastrophically overheated appears to be a surprisingly narrow band of orbital distance, meaning a planet's exact position, sometimes by a margin as small as a few percent of its orbital radius, can be the entire difference between an ocean world and Venus. Hydrogen dominated atmospheres on sub-Neptunes. Here's the reframe. The most common type of exoplanet discovered so far isn't a rocky world at all, or a gas giant like Jupiter. It's something in between, a category with no equivalent anywhere in our own solar system. Sub-Neptunes, planets larger than Earth but smaller than Neptune, frequently retain thick atmospheres dominated by hydrogen and helium, gases so light that a smaller rocky planet like Earth would lose them to space almost immediately, but which a slightly larger planet's gravity is strong enough to hold on to permanently. Here's the fact that should genuinely bother you. This single category, entirely absent from our own solar system, appears to be the single most common type of planet in the galaxy based on current survey data, meaning the most typical planet in the Milky Way looks nothing like any planet humanity has ever directly observed up close. Here's the part that lingers. A thick hydrogen atmosphere on a sub-Neptune can create crushing surface pressure and extreme greenhouse heating regardless of orbital distance, meaning even a sub-Neptune sitting in its star's habitable zone by distance alone could still be completely uninhabitable, buried under an atmosphere so thick and so effective at trapping heat that habitable zone stops being a meaningful description at all. Puffy, low density atmospheres on super puff planets. Here's the fact that reframes what an atmosphere can even weigh. Some confirmed exoplanets have such an extraordinarily low density that their measured mass, combined with their measured size, implies an atmosphere so puffed out and diffuse that the planet has been nicknamed, informally but accurately, a superpuff. Here's the fact that should genuinely bother you. Some of these worlds have an overall density lower than Styrofoam, meaning if you could somehow find an ocean large enough, the entire planet would float. The leading explanation proposes an unusually thick, extended layer of hydrogen and helium, puffed up dramatically by intense heating from a nearby star, creating a planet that is, by volume, almost entirely atmosphere, with a comparatively small, dense core hidden deep inside. Here's the part that lingers. This category was genuinely unexpected when first confirmed, and it directly demonstrates how differently planetary atmospheres can behave once you remove the specific narrow set of conditions that happen to apply to every planet in our own solar system. An atmosphere isn't just a layer of gas sitting on top of a planet. In extreme cases, it can be most of what the planet actually is. Evaporating atmospheres on hot, tightly orbiting exoplanets. Here's the fact that pushes this category toward outright planetary destruction. Some exoplanets orbit so close to their host star that their atmosphere isn't just heated, it's actively being blown away into space, stripped by intense stellar radiation faster than any natural process could replenish it. Astronomers have directly observed extended comet-like tails of escaping gas trailing behind several of these hot, close orbiting planets, visible evidence of an atmosphere in the literal process of being torn off and swept away by its own star. Here's the fact that should genuinely bother you. For some of the most extreme examples, current models suggest the entire atmosphere could be completely stripped away within a timescale of hundreds of millions of years or less, a genuinely short window in astronomical terms, meaning some currently observed puffy or gas-rich planets close to their stars may eventually be reduced to bare, rocky cores once their outer layers finish evaporating entirely. Here's the part that lingers. This process may explain a genuinely strange gap noticed in exoplanet survey data, sometimes called the radius valley, a specific size range where far fewer planets than statistically expected have actually been found. Strong indirect evidence that planets in that in between size range are unstable over long timescales, either holding on to a thick atmosphere and growing into a sub-Neptune, or losing it entirely and shrinking down into a bare, rocky world with very few caught permanently in between. Atmospheres detected through direct spectroscopy. Here's the pivot. Everything described so far was inferred through models and indirect evidence. This category describes the actual method, now allowing astronomers to directly measure what specific gases are present in some exoplanet atmospheres, rather than simply guessing at their broad category. When a planet passes in front of its star, a tiny fraction of the starlight passes directly through the planet's atmosphere on its way to Earth, and specific gases in that atmosphere absorb very specific, identifiable wavelengths of that light, leaving a measurable chemical fingerprint in the starlight astronomers ultimately receive. Here's the fact that should genuinely bother you about how difficult this actually is. The atmospheric signal being measured is an almost impossibly small fraction of the total starlight involved, comparable to trying to detect a firefly's light shining through a spotlight from thousands of kilometers away, which is exactly why this technique has only become reliably possible for a select group of larger, closer, brighter exoplanet systems, generally hot gas giants, orbiting close to their star, where the signal is strong enough to actually separate from the noise. Here's the part that lingers. This exact method has already directly confirmed water vapor, carbon dioxide, methane, and even controversially tentative candidate biosignature gases in a small handful of exoplanet atmospheres, meaning the direct atmospheric chemistry of worlds light years away is no longer purely theoretical. It's becoming an active, growing body of real measured data, atmospheres stripped entirely away, leaving bare rocky worlds. Here's the fact that closes this list on its most stark, most minimal note. Some exoplanets, particularly those orbiting extremely close to small, active red dwarf stars, appear to have no meaningful atmosphere left at all, having had it fully stripped away by intense stellar flares and radiation over the course of their star's lifetime. Here's the fact that should genuinely bother you. Red dwarf stars, the most common type of star in the galaxy, tend to be significantly more magnetically active and prone to intense flares earlier in their lifetime compared to sun-like stars, meaning a planet in the habitable zone of a typical red dwarf, appealingly close and easy to study by orbital distance alone, may have already had any atmosphere it started with stripped away entirely before its star ever settled into a calmer, more stable phase. Here's the part that lingers. Because red dwarfs make up the vast majority of stars in the galaxy, and because their habitable zones sit so close in that planets, they're relatively easy to detect and study compared to Earth-like orbits around sun-like stars. A significant fraction of the most easily studied, potentially habitable exoplanets discovered so far may, on closer atmospheric inspection, turn out to be bare, airless rock, a sobering asterisk attached to some of the most exciting exoplanet headlines of the past decade. Tidally locked atmospheres with permanent day-night extremes. Here's the fact that closes out the category defining atmospheres with one shaped entirely by orbital geometry rather than chemistry. Many rocky planets discovered orbiting close to small, dim red dwarf stars are believed to be tidally locked, meaning the same hemisphere permanently faces the star, while the opposite hemisphere sits in permanent darkness, the same way the moon always shows Earth the same face. Here's the fact that should genuinely bother you. Models suggest a planet in this configuration could develop atmospheric circulation patterns found nowhere in our own solar system, with permanent, ferocious winds constantly transporting heat from the scorched day side to the frozen night side. And in more extreme scenarios, the night side could become cold enough for atmospheric gases to freeze solid directly onto the surface, gradually stripping the atmosphere from one side of the planet and depositing it as literal ice on the other. Here's the part that lingers. Whether a tidally locked planet's atmosphere survives this process intact, redistributes evenly enough to remain habitable across a narrow twilight band between its two extreme hemispheres, or simply collapses entirely onto its permanent night side, appears to depend on a delicate balance of atmospheric thickness and composition that current models still can't confidently predict for any specific planet. Let's sort these 8 again, a different way, not by how Earth-like they are, but by what actually detecting each type required. On the still just out of reach end, a genuine Earth-like atmosphere, a category current instruments are only now approaching the sensitivity to confirm directly on a small rocky world. On the confirmed through direct chemistry end, atmospheres measured by spectroscopy requiring the largest, most sensitive telescopes currently available, but yielding real specific chemical data rather than inference. On the confirmed through modeling end, runaway greenhouse and evaporating atmospheres, both strongly supported by combining a planet's known mass, size, and orbital distance with physical models rather than direct chemical measurement in most cases. On the confirmed through density alone end, sub-Neptune and super-puff atmospheres, identified primarily through the mathematical mismatch between a planet's measured mass and its measured size. And on the confirmed through absence end, bare, stripped rocky worlds, identified partly by the conspicuous telling lack of any atmospheric signal at all, in situations where a thicker one might otherwise be expected. It's worth being honest, before we close, about the single biggest limitation running underneath every category on this list. Almost everything described here comes from studying planets that are easiest to detect and measure, not necessarily planets that are typical. The methods discussed elsewhere on this channel for finding exoplanets are naturally biased toward large planets, close orbits, and bright nearby stars, meaning the atmospheres astronomers have actually managed to characterize in detail so far skew heavily toward hot, gas-rich giants rather than small, temperate, rocky worlds. Here's the fact that should genuinely bother you. This means our current picture of what exoplanet atmospheres are like is built almost entirely from the easiest cases, and the genuinely Earth-like atmosphere every search ultimately hopes to characterize in detail remains, for now, one of the rarest and hardest data points to actually collect. Here's the last thing worth sitting with. Every exoplanet atmosphere on this list was identified without a single spacecraft ever actually reaching the planet in question. Every conclusion came from analyzing starlight, sometimes a firefly's worth of it, passing through or reflecting off a world light years away. We are right now in the earliest years of being able to genuinely know what the sky looks like on another planet using nothing but the light that world's own star happens to send us. Not bad for stick figures on a rock.